So welcome everyone to the spatial data tutorial this afternoon. I feel very honored that I was invited to give this tutorial. I guess the reason was that there's pretty much has changed in the sort of landscape of doing things with spatial, or the possibilities, let's say, the landscape of the possibilities of doing spatial things with data, with spatial data in R. My name is useR, and I'm happy to meet so many of you who I haven't met in real life so far. This is a little overview of the tutorial that I'm giving to you. So a little bit of a history, what preceded where we are now. A little bit about the simple features package. Actually, most of the afternoon I will talk about the simple features package because that is the sort of lot of new things. Things about tidyverse and how that sort of intertwines with simple features. A little bit about reference systems, why they are important and how we deal with them, how we dealt with them, how we deal with them now. And then some examples with simple features and methods for simple features and so on. Yeah, so it's simple features before and after, right? I will explain what simple features are in a few moments. Pi-based workflows I will say a little bit about, and I'll say also a little bit about array data rasters and how that doesn't yet fit in but might fit in the future and so on, and give a summary and outlook at the end. So we have 2 sessions of 1.5 hours. I will try to not do, I will try to not punish you with monologues of 1.5 hours, but the session is not too interactive in the sense that this is not like a practical class. But if you are sort of interested in how all this works, then this is basically, I'm very bad at generating slides, but I can somewhat deal with Markdown, R Markdown, and there is an R Markdown file actually referenced here. So I don't know if you can read this. I think the link, the URL of this document is there in the top, in the URL bar of this screen. And it was also mentioned in the, I think in the tutorial description. I learned that last year. You can try to sort of get in touch with all the participants, but if you know ahead where you're going to put things, then that works better. The R Markdown file is here, so you can load that into something, into RStudio or something, and then actually run it. And that calls for a couple of packages here. It will also install ggplot from GitHub. So if you're scared about that, then don't do it. Right. So spatial data in R new directions. As I said, there's a couple of packages that I will use. I may not use the whole tidyverse, but anyway. Spatial data started pretty early in R. Basically, it started pretty much pre-R, sort of in the time that a lot of people, including me, were using S+ for their daily work for things. And there were a lot of add-on packages in those days in S+ that were later sort of ported to R or also used in both environments for a while. For instance, there's a package called Spatial that is part of MAS, written by Brian Ripley. Brian Ripley wrote also the 1981 volume, Spatial Statistics, the only book with that title, actually, and could write that because he was sort of very much pioneering with using computers to do statistics on spatial data, and wrote all kind of Fortran code for that, and it sort of was moved into MAS. This package is mostly there for historical reasons, and the book may have a chapter on how that works. Spatstat is another very, very large package developed by Adrian Badley, Rolf Turner, and Ege. Are you Ege? Ah, nice meeting you, Ege. And Ege Rubak, who sits there. That is a package that sort of slightly misnamed. It suggested of spatial statistics. It focuses on point patterns. Point patterns is a massive chapter in spatial statistics, and this is actually a huge package which has like 100 contributors or something like that. Anything you want to do with point patterns is there. MapTools was for mapping, GeoR for geostatistics, Planks was a Lancaster sort of point pattern package, GStat is geostatistics, which I sort of developed in the previous life. People were in 2003 put together by an initiative from Roger Bivens. A lot of people met then up in Vienna at the Distributed Statistical Computing Conference, the conference series that preceded useR essentially. And there we sort of had a pre-conference workshop meeting where we kind of came up with the idea, okay, we should do something together in sort of not everyone should make its own assumptions on how spatial data are organized in R. it might make sense to sort of do this in one way and then have packages reuse that. That turned out to be a multiplicator, right? So that ended up in doing a couple of years doing the package SP, and that means that instead of, if you want to go from one package to another package, that you need n² conversions when you have n packages, you now only need to have n or 2n packages. So in terms of scaling up, things became linear instead of quadratic, and that's always a good thing, computer scientists tell me. 2003 also the RCGDAL mailing list was started. RGDAL was already a package that interfaced to the GDAL library. GDAL is an old library, still very actively being developed. And in 2005, I think we released SP to cron. That was mostly Roger Bivet and me, and sort of added SP support to RGDAL. So SP provides classes and methods for spatial data. So it has a very simple idea. Okay, spatial data are either points, lines, polygons, or grids. And that will sort of solve most of your problems. And they did that for quite a long time. In 2008, we wrote this book, Applied Spatial Data Analysis with R, which turned out to be pretty much a bestseller. And then 2011, our GEOS was released that does, it's an interface to the GEOS library that does spatial topology things, right? Do two polygons intersect, there's a point in the polygon, all the complex things that basically we think of as sort of GIS type activities were now possible with R directly on these SP data. And it led us to rewriting or bringing out a second edition of the Applied Spatial Data Analysis with R book. And then recently in 2016, I started with a couple of other people, the project Simple Features for R, which was exactly a year ago I was talking about. It had wild sort of idea architecture diagrams and not a single line of code. And now 1 year later, it's pretty much finished. And that is sort of, I'd spent a lot of hours on that, but also a lot of other people sort of got involved in the development, and it was sort of very extremely helpful. So I think we are now at sort of on GitHub at 400 issues, on average 5 communications per issue, so 2,000 issues in total, messages that sort of, you know, and I have a daily job as well. So it's interesting. It was good fun. And right now I started another project, or I'm going to start and talk about it on tomorrow in the GIS session. That's called Spatial Temporal Tidy Arrays for R, so I will not talk about that too much because my talk tomorrow is about that. Here's a nice graph of a point cloud, so to speak, of R packages that was sort of tweeted by Colin Gillespie. Is Colin here? I think Colin is giving another tutorial. That sort of gives 10,000 packages and uses some script that Andre de Vries from Revolution Analytics published earlier, or I don't know what the company is called today. Microsoft R, I think. That does a point sort of packages, R packages, and how they are connected and what sort of the centers are. And he ended up with these 5 centers, and you see that is about sort of web services, interfaces to C++, applied statistics, and graphics. And there's an SP one, interestingly. And SP is sort of the smallest, but it's the only with a particular domain, interestingly. So there are a lot of packages cohering around this sort of SP cluster that do things with these data. So in that sense, that was, you know, that has served a role and was useful, and it's used by a lot of other packages. So this is not like this is one package. There's a whole sort of package ecosystem around SP, reusing, sort of benefiting from that, doing things. So now why did we come up with a simple feature package? Basically, simple features kind of does the vector, meaning points, lines, polygons part of SP again, but differently. So why is this a good idea? Why should we do things different? It's sort of pretty much different. And that is what I'm going to explain now. Simple features is actually an ISO standard. Yeah? So that means that you can go to ISO in Switzerland and pay 100 Swiss franc for a document there. But you can also go to the OpenGeo Spatial consortium, which has the sort of the pre-official versions of all these documents for free for download. Download doesn't work really well right now. And that isn't, so it's a standard document. It describes how a data type works, what it is, and how it's represented. And it does it pretty well, sort of in contrast to to most of the standard documents that I've tried to read so far. This one is not so bad at all. It's actually, to some extent, it's fun. There were people well aware of computational geometry and so on doing that. That standard sort of came up around 10 years ago. So that came up around the time that we were done with SP, basically, that we have thought, and SP sort of is older and was built on top of the then customary way of exchanging lines and polygons. That was by shapefiles. And shapefiles are, you know, pretty much a nightmare if you think of that sort of today's standards. So this standard actually came up later, and so it didn't align exactly with things we did in SP. And so there is now the opportunity, we thought, to do this better. It is actually used in spatial databases. It's used in GIS, open source libraries, GeoJSON, GeoSpark, also linked open data. All these standards basically use simple features to, if you have points, lines, or polygons, to describe them, yeah, in a standard way. What is it about? Well, it's about features. What is a feature? Features are here defined as things, yeah, so abstractions of real-world phenomena. So think of a building. Yes, a building is a type, so we can have all kinds of buildings. We can also have this building, which is an instance of a building. Yeah? So this building would be a feature. Then a simple feature is seen as a feature where all the geometric attributes, meaning where is this building, are described by piecewise straight line things. Yeah? So we have a couple of points connected by straight lines, and that makes it a simple feature. Of course, this building is not straight. There are no straight buildings. But if we would do that, right, and many architects do that to some extent, then it would be a simple. But it's basically the way we represent it in a computer, by lines with points with straight lines between them. There are quite a few types, and I think I can also not go to this, probably. No, nothing works. That's too bad. Anyway, there's a long list of types, but there's only a short list of 7 that are really essential to them. And yeah, it's coming up. Here are the types. So here we see the 17 types. Yes, we forget for this moment about geometry, which is kind of a superclass, so anything is geometry. But then we have the types. So we see point, line string, which is a set of points with straight lines between them. Polygon, which is basically a ring, so a closed ring, non-self-intersecting, with 0 or more inner rings that are holes. Yeah, so it's one or more rings, where all secondary rings are holes in the outer ring. Multi-point, so set of points. Multi-line string, a set of line strings. Multi-polygon, a set of polygons. And then we have geometry collection, that's a set of anything. So set like a point and a line together. Yeah, it's geometry collection. And then we have the last 10. They are much less interesting, curved and so on, and funny types, but you very rarely see them actually in the wild. So these 7 types, point, line string, polygon, multi-point, multi-line string, multi-polygon, and geometry collection are the most important. And then we have like 4 types in terms of dimensions, in terms of what a single point represents. So typically point is just 2 coordinates, x and y, but it can also have 3 coordinates, 3-dimensional geometry. Like then we have x, y, z, and we can also have like x, y, and a thing they call measure, that is anything, like, well, like maybe the time the point was measured, or a GPS error or something like that. You can sort of, you're free to use that, and it's used very rarely, to be honest. And we have the combination of the 3rd dimension and the measured dimension. Yeah? So there are like 4 instances basically with different definitions of a single point. So the ZM, XYZM geometry for a line string would have a set of points where each point has 4 coordinates, x, y, z, and m. So in total, this sort of brings us to 68 classes. I was like, oh, but basically 7 of them, the x, y, and the first 7 types. Yeah, so this little row here, x, y, the 2-dimensional ones, and these 7 types are really used in the majority of the cases. Doesn't mean that we don't want to sort of implement them all, but there is really support for these 7. So you can think, okay, there's room for 68, but we typically use 7. It comes with text and binary serializations. These are important. I will explain why. And it comes also for support for mixed types. As I said, geometry collections. Something has a geometry that is a point and a line and a polygon. We'll give examples. And we can have like mixes, like we have 2 features, and one feature is a point and another feature is a line, and have to deal with that. And there is also support for the empty geometry, meaning the empty set, really. Yeah, so think of the NA, the missing value in in regular data, we can have sort of empty geometries, which is actually a very nice thing to have, and that SP, for instance, does not have. It does not have infrastructure for empty anything. So here we start by loading the library, and it gives this long message that I'm going to link to here to 4 external libraries, right? So this is pretty scary. So what it does here directly is it links to the geos library for geometrical operations, topological operations, to GDAL, which is a library for reading and writing, like 70 different formats and databases and web services and everything, and to the Proj4 library, which is a library that does cartographic projections and datum transformations. I will talk more about that. This is not always, this is not like a cron package will not do that. This is sort of an extra thing. The Elway lightweight geometry library is basically the library, the C library that PostGIS is built upon. So that adds a lot of additional, maybe useful things that I'm sort of experimenting with. Yeah, but that you will not really miss if your version does not do that. That's not so bad. So these are basically, so this is basically an interface package that has like whatever, 7,000 lines of code or something, but that really links to a lot of other code that is on all these packages, and it is well tested, and it is used in all other environments like Quantum GIS, like PostGIS, like all the open source sort of train of things that we now basically draw into an R session by this single command. So that also we had RGDAL, we had RGeos in the past. That is kind of forget that. Not completely forget, but it is kind of replaces that. Simple feature access means really that we use standardized encodings, right? So that we have ways to read and write and to communicate these data. So one encoding is the well-known text encoding, WKT, and that looks like this. Yeah, so there is, if I create with my R function a point that has 2 coordinates, 2 and 4, you get this, it's echoed like this. We get a well-known text, a variety of that echoed. I can also write that to character strings and export it as text and so on. Another thing is that is the well-known binary, and well-known binary is basically a binary serialization of this same thing. We see that here the SDS binary of this point, so I'm going to convert this point to binary, is given here. So this is a raw vector, and that I by now can kind of read them. And you also see the same point actually used here, and also the binary encoding of this 2-4 point. And you see here that here they're nicely colored. It starts with 0 for the endian, so this is big endian, then 1 for the type 1. Oh yes, that is point. And point XY, yes, point XYZ would be 101. And then we get these 2 numbers, which are the 2 and the 4 in 8-byte double representation. Of course, this is hexadecimal, right? But R basically gives us the same, which is this, except that, of course, I have a little endian machine, so the bytes are swapped, right? So I get a 0, 1, little endian, and then I get a 1 binary 4-byte integer of value 1, which is, little endians, so it's reversed, and then I get these 2, these 2 8-byte doubles here, right? And that is to some extent important, that I will just explain. Yeah, that is basically said on the next line. So this binary form is essentially what spatial databases put in the database, yes? And if you don't believe that, I have a database open here, a database called PostGIS, yes, which is an extension to PostgreSQL, and there are 2 tables in here. And if I say select star from F, this is a database with point data, give me the first 3 records, you see here that I get all these records. It doesn't sort of print nicely on a single line. Maybe it does like this. Make it very wide. Yes, nice wide screen. So you see the sort of zinc and values and so on that we also used in the book, the Springer book, and you see here this column WKB geometry called that has this hexadecimal blobs. Yes, they're binary large objects, and they're exactly identical in terms of the representation as the binary raw object that we just saw here. And I can, of course, Postgres can also say, well, this is unreadable, so give me the ST as text representation of this column, and then you see the well-known text representation, right? That you could, you know, put in your whatever linked open data or something like that. Yeah, this is human readable, and the binary is much harder to human read, right? And so I can go back and forth, and I can sort of convert this binary blob, which I got here, I can convert it back to an SFC, so to a simple feature geometry, and I get back my point. So I did a round trip now to binary and back. Yeah, so this is all in R. It's actually all written in C++ to make it performant, but I remain in R. And this means that I can write and read this binary stuff. So I can, in principle, just with a DBI connection or PostgreSQL connection, I can read my Postgres or spatial database data and actually parse these blobs. Yes, because I get them as either as raw data, depending on the library, so either you get them as raw or you get them as character data in hexadecimal strings, and you can convert that into raw and then read that. So you can read and write spatial databases essentially without needing RGDAL. RGDAL does a good job, but this is another way to do that. Right. So yeah, and then there are all kind of functions that the package offers. For instance, here one is stDimension that says, okay, what is the dimension of a point? And the dimension is 0. And stIntersects is a function that says, okay, if I have two geometries, are they intersecting? Well, a point, yes, the point intersects with itself, and give me this is a dense matrix, so it's a 1-by-1 matrix that says, true, yes, there is an intersection between these 2 points. So the fun thing is that these functions, the dimension and intersects, they're also prescribed by the simple feature standard. So the axis refers to I/O, but also refers to operations on these geometries. There's a whole list of things that spatial databases implement, and that the SF package also implements. Yeah? So you can see it a little bit as a sort of a PostGIS in memory using R syntax. Yeah? So as a kind of a metaphor, if you like. Of course, PostGIS is much more powerful and does more things, but that is sort of broadly the idea. But then SF uses really native R structures to actually store geometries, and we can see that here, that if I sort of ask for the structure of this point object, I see, well, this is a numeric vector with 2 numbers. If I would create a polygon, I would see that what I get back is a list with a matrix, right? A matrix with 4 rows and 2 columns. The rows form the points in the ring that I have here. And then there's this funny class attribute. Here it says I'm XY point and simple feature geometry. And here it says I'm XY and polygon and simple feature geometry. And there was a little bit of a, it was kind of a little bit of a struggle, a sort of compromise. I had some good help from Hadley Wickham on choosing this. The good thing about saying, well, it's XY and polygon is that I don't have to come up with 68 classes to do this table, but only 17 plus 4, because I basically split the dimension, whether it's XY or XYZ, and I have a class for what type it is, right? So I don't make a single type that says, I'm a polygon XYZ, and I'm a polygon XYZM. Then you would end up with 68 classes, and that is a sort of a pretty much a nightmare to program against, to every time write 68 methods for things and so on. So this is a sort of a very nice shortcut. You can look at what the dimension is of coordinates, and you can look at actually what type it is, because all the polygons, of course, are lists of matrices. Yeah, we will see. So now where comes the tidyverse in. So this was one of the, I'm not sure if this was one of the goals, but we ended up doing, yeah, I think this was one of the goals, yes. Yeah, let me say a little bit, so how SP worked. So SP was a package that was built on S4 classes. 2003, 2004, that seemed a very good idea. There was, Bioconductor was doing that, and it was the new, there was the new the new thing. The Green Book was just out, and everyone was like, "Hey, hooray! We can do serious object orientation here with R, right?" And so we were going to do that. That worked well in the sense that you can have more complex class hierarchies, and You can do method dispatch on multiple arguments and so on. So it has a couple of nice properties. Then came tidyverse, and tidyverse said, well, you know, I'm okay that sort of you have like a spatial points data frame. That was sort of what a points with attributes object was called, and that your object acts as if a data frame, right? You can do square bracket selection, you can dollar selection, all the kind of things that data frames also do, and that works. But it, you know, it doesn't care less. Basically, what tidyverse does is pushes everything into C++, and then it assumes the thing is a list of columns. And then you need to be, right, you're gone. If you have like an S4 object that is kind of everything with slots and so on, it's not like that, right? So that doesn't work. So there were some, you know, kind of mismatches in the sense of the type of assumptions you make, right? When you say something is a data frame, what does it mean? Does it behave like a data frame, or is it really a list of equally sized columns? Those are sort of different assumptions. We were on the other side with SP, and now with SF, we are on this side. We are basically on the data frame side, or table side, whatever, doesn't matter. Tidy data says, the famous Hadley-Wickham 2014 Journal of Statistical Software paper, highly recommended, short title, provocative, and so on. It says each variable forms a column, each observation forms a row, each type of observation unit forms a table. Okay, so we have tables, we have sort of observations in columns. So not like, you know, put your data two-way tables or three-way tables into complex thing. No, just put all the records sort of in a long, unnormalized sort of form. Denormalized is it, I think, called in database language. It's actually not so clear how this really maps into what you would do with geometries, right? So if you have an observation with a polygon, and several polygons, and inside these polygons you have holes and so on, there's a whole bunch of things that, you know, how you're going to put that in a row or so, right? It's not like an observation, it's a pretty complex structure. So, so there were sort of early attempts on doing that, and that didn't work out so well. So if you have like point data, you could say, well, okay, I have latitude in the column and longitude in the column. Well, that kind of works nice, but hey, they're not really like two columns, right? It's really the combination of this point that forms the observation. It's a two-dimensional observation, really. So it's not like two variables that you measure in that sense. Doing things with spatial data and tidyverse, in particular with ggplot, required you to use this fortify idea, which basically creates long, denormalized tables from polygon data, and does that in a way that is sort of well known to fail on a large number of cases where you have holes in your polygons. Because this is way too much administration that you can't put things, you can't put polygons reasonably in a column. Nobody does that. Yes? So the fortify approach, I think that polygons was one of the motivations actually for Hadley-Wickham to give up this requirement that a cell in a data frame needs to be a single value, but that a cell basically, if you use a list column, that a cell might also be something more complicated. And nowadays we have nested data frames, so nested data frames have really sort of single records or new data frames, or they're, for instance, LM objects or something like that. But they, in our case, they can also be geometries, right? So we put geometry in a list column that has the same length of the rest of the attributes, the rest of the properties of our features, and put them in data frames. Yeah? So the list column was basically the opening, the way to reasonably put simple features into these kind of structures. So we have now data frames or tables or whatever, where basically features form a row. Each feature forms a row, right? And that is essentially the same thing that I just showed you here in the PostGIS database, where we also see that we have rows and we have geometry just in a blob, in a binary large object. So how then do we store? As I already showed a couple of examples, we store them in R, native R, as simple as possible. And to my sort of, as I proposed last year, we actually now did that like this. We say a point is a numeric vector. If we have sets of points, we put them in a matrix, like multipoint or line string. If we have like sets of these, right, then we take a list of matrices, yeah, for sets of sets of points. And then we have sets of those, then we have a list of lists of matrices, right, multi-polygons. It sounds extremely convoluted, but if you think about it, if you would do it, there is no simpler way than doing it. Single sets of points are matrices, sets of anything else are lists. Yes, so R doesn't have sort of simpler infrastructure above. And then geometry collections are a list of anything, yeah, but then a typed anything. So geometry collection, of course, needs to know from its list elements whether is this a point, is this a line string, and so on. So these need to be typed. Other tidy aspects in the terms of the design of the simple feature package were that all the functions start with st underscore, that is basically borrowed from PostGIS, which also does that. It turns out that the st stands for spatiotemporal. We need to do a little bit of digging into history where it comes from. It stands for spatiotemporal, which is interesting because they had sort of back then the ambition to do, well, let's do space first and then do space-time, and they never got around to do space-time because it's so much more complicated. But we will do that, yes, of course. So keep it in mind, right? ST is for space-time. We're not just done with features. It uses underscore to separate words, and it uses lowercase for function names. All functions use data as first argument, so they're kind of pipe friendly. So if you can read piped statements, then you can also use them. There is a sort of tidy version of the read, st underscore read. It's also a read underscore sf variety because all the tidy read functions start with read underscore. So you could do read underscore tap tap, and you see all these things. Oh, it's an sf method. And that is silent and uses strings as vectors. It's false. And a lot of the tidyverse verbs are actually implemented for sf methods. You would think, why is that necessary? Well, it's necessary if you don't do it. If you let dplyr do things with your objects, then it just returns tibbles all the time, right? And tibbles are nice, but tibbles don't know which column is their geometry column. So if you have, for instance, 2 geometry columns, and you want to plot a map, what to do, right? So there's things that SF does, like keeping track of, what is my geometry column. That is actually quite nice in sort of data management. And then you have to make sure that when the dplyr method comes back, that the object is again converted into an SF object, right? An SF table or an SF data frame. It doesn't matter. And some of the things are also special, as we will look later on. So for instance, the summarize verb does a grouped summary, for instance, and if you want to have grouped summaries, you also would often like to union the set of polygons that you summarize, right? So if you do something for like 5 polygons, that you sort of resolve the internal boundaries. So that is the default behavior. That is feels kind of natural. But you can also say that it doesn't need to do it. Then we end up with the reference systems part, and that is maybe the most important part, and sort of the most important part also why this was a good idea to not let the data scientists do spatial, because data scientists know a lot of everything and just not nearly enough about reference systems, and they are tricky, and there are tricky things of them, right? So we have people often think, okay, I have latitude, longitude, so I'm done, right? I'm done about it. Well, you're not done, right? Latitude, longitudes can mean different things. It depends. They're basically properties of a model of an ellipsoid or a sphere of the Earth, and there are different models of the Earth. Yeah, there's a global model, WGS 84. There's like local model, like ETRS 89, which is fixed to the European plate, right? So the ETRS 89 has no problems with plate tectonics, which is very convenient. The North American datum also has no problem because it moves along with that plate. Yes, of course, this is not about huge amounts, but depending on what you look at, this matters tens or hundreds of meters or so. So if you look at global maps, okay, that might work. You might not have a problem. But if you know that information, basically you need to keep track of it. Then there's ordering of coordinates. You can have longitude, latitude, or latitude, longitude. That is not something that sort of the general world has agreed upon what a good way is. The Cartesian coordinates. So we have datums, and then we have projected coordinates like in UTM or Web Mercator or things, and there things have measurement units, so is this in meters or kilometers or in feet or something like that. And you need to know how that sort of relates to latitude, longitude coordinates, because you might end up with another map that's in another projection, and you need to combine the two, right? So they have coordinates in different systems, and you have to bring them to a single system in order to make a meaningful connection. So this is what, of course, what GIS has been good at all the time, and with geodesists, they live from this, essentially. What we do is that we build on the Proj4 library to do all this for us, and that is widely used and actually actively maintained. It has been rejuvenated pretty strongly recently, and improved things, and this is well kept. So there's also like in our package that is called like, I think it's like called projection or so, or project, MapProj or something like that, which has a long list of, that a lot of people like that package because it doesn't, you don't need SP and RGDAL and things, or here simple features with its dependencies, but it's basically a bunch of projections that somebody wrote like 20 or 25 years ago, and it has never been maintained since, right? And the world has moved on in terms of, there are a lot of other projections, and there are a lot of insights and better conversions and so on. So Proj4 is really the code that you really want to sort of work with, yes, to do things. Yeah, well, there's nothing better on earth, really. Open source. There is in the simple feature package, there is a CRS object. SP also had it. It was slightly different. I think maybe CRS with capitals or so. But anyway, this is simply a list. If I create an CRS object with ST-CRS, and I give it a Proj4 string, the one for the WGS84 geographic coordinates, I get this object back. It says, okay, you have an EPSG code, so it can resolve that. Doesn't do that always correct. It doesn't do that always, but quite often it manages. It has this Proj4 string, which I fed it with, and so it is well established, right? And it has a class. I can also directly give it EPSG code. So EPSG is basically a database of well-known, defined, and sort of projections that have a clear provenance. Yeah, there's an EPSG database and groups that sort of decide what goes in, what goes out, and whether things change or not. Anything changes. The world changes. There's a problem. Sea level changes, so meaning mean sea level changes. Plate tectonics move and so on. So the world is a dynamic thing. So you need to update things now and then. WGS also has a couple of iterations. There is not one WGS 84. There is already the third version or something like that. This is the Web Mercator thing, and basically what happens here is that this code, the EPSG code, is being resolved from the database, so I get the corresponding Proj4 string for free on that. And there is a dollar method that basically extracts elements of this string, so if there's a unit, it says, I have units, meters, then it can give me the unit as a character string back. So I can query like elements of that. And importantly, there's an NA coordinate reference system, right? The coordinate reference system might be missing. You might be a brain surgeon working with brain images, and you don't want to sort of geo-reference, right? You don't want to reference your spatial data. It's spatial, but it's not so interesting where it was taken. The reference is the skull and the patient, and not so much the location of the scanner, right? So this makes the software useful for domains where the geo is not so important. Yeah, that's why we also often talk about spatial data and as a sort of generic class over geospatial data. So coordinate reference systems are there in part of geometry list columns. Okay. So that was a lot of information. So are there any, before I continue, are there like any questions of general nature or related to what I said so far? Yes?
I was wondering what's the advantage of storing simple features as R objects instead of just storing the well-known text? How
Yeah, good.
is it costly to deserialize the well-known text?
Good. The question is, why don't you store these things as text, like the well-known text representation, so we can read them? Or the binary. I would then opt for the binary because that is lossless. Text always has this problem, like how many digits is, when I go read and write, is it exactly the same thing? And it is more, it takes time. I think, yeah, you could do that. The thing is that that in any case you want to be able to look at them, right? But you could say, okay, I can look at the text version. Then somebody wants to do something with the data, right? And you have a raw vector, And then you think, okay, but where are my x coordinates, right? So it is more friendly, let's say, for people who not just want to sort of, not end users of all these, you know, slick functions, but people who want to sort of do something with it, like write their own plotting routine or projection routines or something like that, and want to sort of get to the real data of the coordinates. And now you can get to the real data because there are structures. And yeah, you could do that. There's another package called RGDAL2, which is on GitHub, written by Tim Keat, the original writer of RGDAL also, that says, well, I'm going to open these things and just have external pointers to structures in the GDAL library because my features are there. Why would I import them in R? And you can do that, yes. But I don't think that was sort of a very sort of user-friendly way, right? It doesn't represent them in R. So if you want to get them, you get them as very convoluted nested lists without any types or something like that. But yeah, this would have been an alternative an alternative approach. I also, yeah, and to make specific, the serialization and deserialization is extremely fast because it's of course binary to binary. So a double is a double. There's no conversion. Yeah, so it's not. There's essentially no conversion. There's just movement of memory, which is just really fast. So there have been reports that, yes, SF in reading data is actually things like 20 to 100 times as fast as RGDAL. And that might be because it doesn't loop over constructing S4 things and construct things, but basically reads in binary data and has a very fast conversion, all in C++. Yes. Volumetric kind of data. Right. Yeah. Yes and no. Rather no and yes. Yes. So points can be three-dimensional. Yes, can be X, Y, Z. So anything you put in can be X, Y, Z. But the dominant, sort of the large amount of the operations really work on the X and Y, and not so much on the Z. So we don't have like three-dimensional intersections of a line and a three-dimensional volume or something like that. There is like the GEOS library is just two-dimensional topology. Yeah, so dominantly the functionality is two-dimensional. Yeah, regrettably. Yes. But yeah, I haven't also not tried or let's say thought very much about the limitations in that sense. But don't count on too much on real 3D support. PostGIS has the same thing. Also uses GEOS for the. It uses the same library for the topology things. It's also 2D oriented. Yeah, what you use? Yes. Right. So that was it. Other questions? Yes.
So is there a way of specifying the operations that will be done to a set of geometries when you do a loopback?
Well, it does the union of anything. So it says summarize. If I summarize a group, basically you go from a set of observations to a single number, and the geometries goes from a set of geometry to a single geometry by unioning them. I'll get to the intersections. Yeah, you can do that, but that's a different activity. Yeah, yeah. Any other questions? Okay. Good. Okay, so we go into some real stuff now. Yeah, and I'm almost at the end, it looks here. So this is still, right. So I go to my local copy of this same thing because this is not going to download by the end of the day. Yeah, so reference system in that sense are important that they give us anchor points. Yes, they tell us what the meaning of a number is. The same thing as measurement units for a value, right? If you have a length in meters and kilometers, you're not supposed to add them without a unit conversion. Doesn't make sense. And the same thing is for reference system for spatial data, for coordinates. Without reference system, you're lost. And here's a unified framework that pretty well deals with a lot of cases. Now we're going to look at how sort of reading data looks like. right? Here I load a test data set that is present in the package. So if you install the package, it's also on your computer. It looks funny, but this basically says, where on my system is this shapefile? Yes, well, here it is. Then I say, okay, here's the shapefile. You get a long name, and you say read as fname, and it's red, right? So this is quite different from RGDAL. It needs only one name, although RGDAL has moved in the same direction. It sort of accepts, okay, there's a shapefile. Let's read the shapefile. Although the shapefile has always 3 or 4 files. It just does that, and it gives you a report then, and so a bit longer report. I said, now print it with only 3 observations, and gives this header, and that says, I'm 100 features with 14 fields, so meaning 14 attributes, yes, and the feature implies that there's also geometry. It doesn't say so, but then says the geometry type is multi-polygon, right? So I have states with single and with more than one polygon. As you can see here, there's a couple of states with counties with islands. This is one state, North Carolina. Dimension is 2, dimension xy, and it has the bounding box, and it has the coordinate reference system information, the SRID if present, and the proj4 string. And here you already see a nice example of longitude, latitude data on non-WGS84 datum. So this is the North American datum 1927 that is still in use a lot for a lot of data. And then it gives you a print, basically what we know from data frames, how data frames are printed. And if it's a tibble, it looks different, looks like a tibble. And you see that nicely the geometry column is kind of abbreviated, right? So I get the first little bit of the well-known text, because the whole well-known text is, of course, a very long string with all the points and rings and everything. Yeah? So it abbreviates that. And then if I say plot, it is the same idea. If you say plot to a data frame, it gives this scatter plot matrix. It basically gives an impression of the whole data set. And it says here, oh, okay, I'm going to do 10 attributes. Because if there are 140 attributes, you don't want to have 140 maps. But it gives a handful, and doesn't give legends, which is, of course, makes it pretty useless to some extent. But in any case, it distinguishes between continuous and categorical variables, right? The categorical are in these nice colors. These colors are also nice, but I like these more. They're good. The color brewer is the name of the package that did that. Color brewer palette. Coordinate transformations I can do then, yeah. So these are in NAD 27 latitude longitudes. I want to work from now on. I want to work with projected coordinates, and I can do different things. There are 2 projections actually, but in particularly developed for the North Carolina, called the North Carolina State Plane, which is apparently states develop their own projection standards projections, and there's 2 of them. One says, I am state plane in meters, and the other one says, I'm state plane in US feet. And if I transform them to those projections, and do that for the first county only, here you see subset, square bracket is subset for those in tidyverse who have never sort of run into a square bracket subsetting. You can do a pipe and a filter, yes. You can do pipe and filter. I have a select filter, pipe and filter, but you can also do a subset, which is actually shorter code. And then transform this. So this is transformed. And then I compute the area. And the funny thing is that you get a number back, and you get the measurement units back. Yeah? So this uses the units package that actually sort of cleverly deals with measurement units. It knows measurement units because they are in my coordinate reference systems that registers. Well, this doesn't. This is latitude, longitude, but then there's a package geosphere that actually computes the area from a polygon on an ellipsoid, right? So you can do that. It's a bit of math, but somebody programmed that, so it's there. And you get an area back in square meters. And here, so this is also, but this is projected. So this is a flat area, which is much simpler. Geos does that for you. And because it's 2-dimensional, you get an area back. And you see that they're pretty similar, but then from the 5th digit on, they differ, right? So they're different numbers, have to be different numbers. I don't think it has to be. If we had used the projection that preserved area, it would have been identical, but this projection actually is an LCC, Lambert conformal conic, Lambert conformoconic, that doesn't preserve area, so it's pretty good, but it's a different number. And this one gives me a square US survey foot back, and if I compare all these three numbers and convert them with the conversion method in the units package, I get them in square kilometers, and you can see the three numbers and you see that A2 and 3 are identical. Of course, they're the same projection, they just have different measurement units, so converted to square kilometer, they're identical, and the one that does this on the ellipsoid gives a different number. So here you see a nice integration of measurement units, because it's always like, you know, these numbers, and what are these, meters or some, and then they're latitudes, longitudes, and you say something, you give some parameter, but what does it mean, right? What does it do? Is this like a degree, but a degree, you know, a degree longitude is pretty different depending where you are, right? How close to the equator you are. So that's problematic. From here on, I'm going to say I'm transforming my data sets, and it will continue with transformed coordinates to avoid that I get a lot of warnings later on. There are a lot of methods implemented, like intersection and so on, that actually work for two-dimensional data. If I throw in latitude, longitude data in that, it quite often works well, yes, but not always. And R cannot tell when it works and when it doesn't work. At least we're not that clever, right? So you always get a warning if you do things along with your latitude data that assumes they're actually flat data, you get a warning, right? So to get rid of these warnings, I'm going to continue with projected data here. There's a whole bunch of methods that work. This is a command that you could use to find them out. You see the whole list of methods, and some of them we will run into, and some of them are completely boring. But you can basically find out by what is there in addition to doing ST. Oh, I thought ST tab would. Oh, this is yeah. ST tab gives you these lists, but I'm not good at RStudio. So it gives you this list that you have to scroll through. I'm just used to the overview that Bash gives you. But, right. So yeah. So there's all these methods, and I will go through a couple of these methods. We already saw quite a few. Yes, there is the low-level things, the bookkeeping things, STS text convert to well-known text, as binary convert to well-known binary, STS SFC converts back into SF geometries, right? The SFC object is the geometry column, right? For instance, from text or well-known binary, or also from other things. Then there is the back and forth to SP, right? So SF has methods. You say if I have an object X that's an SF object, you say, well, convert it to spatial, and it will try to convert it to spatial. If it can. There are cases where it can't. If it is mixes of points and lines, what to do, right? Spatial can't do that. If these are empty, I would be curious what would come out. Actually, I don't know. In any case, yeah, you can convert things to. So if you are like, you know, questions people ask, like, can I use this with raster and so on? No, you can't use this with raster, but raster uses spatial things, and there's a sort of, it's a pretty short command to convert, and it doesn't really take time or so to do that, to go back and forth. And in many cases, it's lossless. Yes, it is sort of, you don't lose anything. You only lose things. SP does not represent, for instance, the difference between lines and multi-lines, or between polygons and multi-polygons. Everything is a multi-polygon. So if you have like a mix of polygons and multi-polygons, convert them to SP, everything is a multi-polygon, you convert it back, everything is a multi-polygon. So you lost that there. So these round trips are not one-to-one because the data model is different. The data model of SF is larger. It's much more possible than in SP. But of course, SP covers like 99% of the use cases. So like, is this really sort of a real issue or not? You have to think. Now we come to the intersect things, right? So now we come to more interesting sort of JS type analysis queries that you can do. And this is a list of all the binary geometry predicates, yes? So predicates in the sense that they yield a true or false. Yeah? So ST intersects for two geometries says, do these two geometries overlap? Yes, and gives you a true or false. And these are all predicates. Disjoint is the negation of intersects. Touch is due to things touch each other, meaning they don't overlap, because overlap is not touching. Do they cross like two lines? Do they cross? Is one contained within the other one, or does one contain another one? Do they overlap, meaning their intersection is at least is more than one dimension, is two-dimensional, is a surface, covers and is covered by, and equals. Equals exact is a funny thing. Better forget about it. Spend a lot of time to. Equals exact really looks that they are exact in the sense that they are the same sequence of points. You can have two polygons, rings, that basically start somewhere else, and they are equal, yes, in terms of ST equals, but they're not equal in the sense of ST equals exact. So yeah, it's cost me like 2 or 3 hours this weekend to find it out. That's a nightmare. Anyway, good. What does this function give? Basically, they do things for pairs of geometries, right? So typically we work with sets of features, right? A whole table of counties, or a whole table of whatever district, administrative district is quite typical, or the set of points. Want to know what intersects with what. Pairwise true and false, you would think, okay, this gives a logical matrix back, and you can get that logical matrix back, like here, if you say sparse is false, but you typically do not get it back. You get, by default, you get the sparse representation back with only the indexes of the things where you have it true. And the big advantage there is that if n is large, if you have like 100 million of points and 10,000 of administrative regions, the dense matrix, logical matrix, would be 100 million by 10,000, right? So it would blow up your R session and jump out of memory. But you will have very little sort of intersections, because every point falls only in one polygon. So the sparse representation is really a saver here, sort of a space saver. And it's also a list column with indexes, so you can put it again in principle in a list column of your resulting structure. But you need to be aware that if you later on then do a filter, right? So you filter records, that these are essentially references to other records. And if you do a filter and filter out some records, then these references are no longer valid. Yeah, so this is a pointer to record 1 and record 2, record 1, 2, and 3. Yeah, so if you want to filter this later on, you also need to recompute all the indexes, yeah, which is, you can think about it. Yeah, so this is questionable whether that would be a good strategy. But anyway, you can find neighbors, you can find intersecting geometries, and so on. A couple of other things. I will just in a moment show an example of this. This is a bit more exciting. A couple of other things that are binary operators that result in a geometry, right? So this is a predicate, this results in a true or false, and some things result in a geometry. For instance, the union of two geometries, right? So the union of two polygons is a multi-polygon of these two polygons. 2 points is a multi-point, and so on. And if I have a union of two overlapping polygons, I get a single polygon with the resolved sort of inner boundaries back. That is what union does. Intersection gives you all the pairwise intersections. Yes, and there was a very nice question on Stack Overflow that I discovered and spent out of way too much time on the weekend on, that if you have like 3 overlapping things, right, 3 overlapping circles, then you have like, there is the sort of the circles themselves and the intersections with themselves, and then there is the intersection with the neighbors, so you get 3 intersections, and the middle part is basically covered by 3 of the pairwise intersections. So it is not like you do this higher order, you do this really bivariate, and then when you want to do it higher order, it's not easy. Intersection does intersections. Difference, like when I subtract an area from another area, I have 2 overlapping things. I will sort of cut out the half from another part and keep that. You do that with difference, and sim difference is the symmetric difference, which basically XOR. So here is an example where I do some of that. What do I do here? Give me 2 plots, base plot, some base simple things. Plot these 3 counties. These are the first 3 North Carolina counties. And compute the union. That's what happens here. Plot the union with the line width 2. So this is the thick black line. So you see here the union polygon inner boundaries are resolved. And I can, for instance, also ask for the intersection between the first county and the second county, right? And plot it as red. Oh, I wouldn't know how to do that with ggplot. But with base plot, this is very easy. And you can say add is true, and then click, there's the red line, right? Ah, there is a red line. And here I did some buffering, that is the next thing, buffering with a positive buffer that gives me the blue line. Of course, this is cut off by the plotting region, right? So this is not like, it goes on here, but this is sort of outside my plot boundary because I did it in the wrong order. So a positive and a negative buffer gives me the green line. So this is like buffers you can use, for instance, if you want to sort of do distance things, right? So if you want to do an intersection of anything or find things that are within like 10 kilometers of another thing, you do the buffer of the first thing 10 kilometers and intersect it with the other things and find things within a certain distance, right? So they are a useful tool. Also, they're pretty useful if your geometries are invalid, are sort of self-intersecting, as the buffer seems to be a pretty good recipe to get rid of those kind of problems. What are these things actually good for? They are, you know, this is a lot of like, you know, mathematicians, people who like computational geometry doing fun stuff and so on, because these like, you know, these are kind of all verbs, but they're pretty like low level, and you get this like, this really looks like programming, right? The things you get back. But the actual work that many people often do is much more like on a higher level, like grouping things or cutting out things or putting things together, summarizing things. So these functions are basically sort of being reused in a couple of higher level functions that I will now demonstrate. Here is one, it's called an aggregate method, which basically is, aggregate is a base R method that basically does group by and summarize in one pass, right? So aggregation says, what do you want to aggregate? What is your aggregation predicate? So your grouping thing, how do you group things? What's your aggregation function? Which function should I use to group things? Yeah, so it says group by, summarize, which you quite often do in one step. And so summarize does basically the same thing. They both use ST union. By default, you can put it off, but by default, it's on to group featured geometries, right? You aggregate them, get something new. There's an example here. Let me see. No, example comes later. I will show the example later on. Here's an example of a function that I called st interpolate underscore AW, where AW stands for area weighted. Yeah, I wasn't brave enough to write it completely out as a single function. That is kind of my weakness. It's not very tidy. Area weighted interpolation kind of lets you go from a certain values in certain areas to values new spatial areas, right? So here is a simple example. I have these counties, yes, with the data that we saw here, right? So these kind of data, county-wise properties, and I want to sort of have them on a different spatial resolution, basically for these grid cells, these dark gray grid cells, right? This is, SF can do nothing with grids, but of course grids, you can see grids as sort of collections of little square or rectangular polygons, which is what they did here, right? Don't tell Robert Heijmans. But it's the same thing. So these are basically little square polygons that you can then work with. And now I want to sort of redistribute anything that is in a county to a polygon. Well, it depends. Redistribute. I want to sort of have a value. And now this function actually takes two paths. It has a compulsory argument called extensive, where you have to tell whether the variable you're interpolating is extensive or intensive. Yes, who is familiar with that concept of extensive or intensive variables? Somewhat, yes, good, quite a few, yeah, that's good. So there's a difference between variables if you I think extensive variables are the variables that if you have something, you cut it in two, that the value also cuts in two, falls in half, right? So you have like mass of a stone, you cut a stone in half, you have two half masses. Another thing is like density of the stone, right? Or temperature of the stone. If you cut a stone in half, same values, right? Doesn't change. So some properties change by redistributing, other properties don't change by redistributing. Interestingly enough, all our databases and so on never tell us. You know, from a lot of variables, you basically know, right, what it is. Population counts, yes, I'm not going to interpolate that. So you can, if you're going to from one spatial units to another, you can basically do two things. Interpolate, say, well, I'm going to area weight, but I don't care that the total is preserved. And the other one is that you basically say, I'm going to redistribute. Yes, that is what you do for extensive variables. And so you weight basically over a different number, the sum of the original values. And the outcome then you see here, and you see this is the extensive area-weighted interpolation, this is the intensive, and this was apparently the state with the highest. This is birth numbers, so birth counts. This is a count, this is an extensive variable. And you see that this state apparently had the highest births, and they're all assigned to this value, and here they're redistributed over different grid cells. And you see that if you do a check afterwards, you can see that assuming things are intensive, yes, extensive is false, meaning they're intensive, that the sum of my original values and the sum of the interpolated values sort of differs with 20%. Whereas if I say it's extensive, I have to compensate for the amount that I have and sort of keep that, use another distribution rule, then you see that the sum of the values of the original counties equals the sum of the values over the new areas. Yeah? So that's a different procedure. That is, one or the other is right. Can't be both. So this is a fun function that lets you go from one. And there already, I saw already packages, I think it's called Tidy Census, a package by Kyle Walker that does all kinds of things with census data, redistributing to new units, and cleverly using this fact that you can either redistribute or basically interpolate. Right? So that is nice. What you also see here, actually, which is much more exciting to some of you, is that there is a proper ggplot of ggplot2 plot, I must say, of these final data that we see here, a faceted plot with two different cases with a single legend, which is very nice to have. And in addition, that this ggplot has these kind of nice degrees, labels, and that you also see that the white lines on the background, maybe you didn't even see it, but the white lines are no longer straight, yes? But the white lines on the background are so-called graticules. They're values with equal latitude and longitude. So they're basically a latitude-longitude grid on the fly reprojected to the projection of this data, the North Carolina State Plane projection. So that is quite nice. There was quite a bit of interaction. The labels here are actually computed in SF. The graticules are computed and reprojected in SF, and ggplot does the logic of basically calling the functions. And actually all the grid functions to plot all the polygons are also provided by SF. So there are some strong, so we had some intensive collaboration on that. The funny thing was that sort of the plotting maps really kind of more or less broke up the whole grammar of graphics logic, because latitude and longitude are not two independent things, really. They are, in terms of maps, they are not like, you know, features that you can spontaneously move or scale or something like that. Just their scaling is very much important for the things that you do. Right? So you always need to make sure that 1 unit north equals 1 unit south, west, and so on. And so that was an interesting interaction. This is supported only by, as mentioned here, by the ggplot2 version on GitHub, which is very easy to install because it doesn't require you to compile anything or so. But not the GitHub version. Not the cron version of ggplot yet. Right. And so are there any questions about that so far? Good. Anything? Yeah.
You have an SF object. Is there a way of just plotting the geometry without, the default plot is to plot the attribute?
Right. Right. You can just. I go back to my. yeah, so plotting as an SF object is indeed sort of, is like plotting a data frame. It's all kind of things. If I want to sort of have the same thing that SP did, SP would only plot with a plot object would only plot the geometry. You can ask for the geometry. You can say ST geometry, and ST geometry gives you an object of class SFC, right? Which is the list column. Yeah, so it takes out the geometry list column, and that has its own class. And if I plot that thing, then you see that you get basically the geometry plotted without any, and then you can start, adding colors and do things and so on. So that basically replaces a plot object in SP. Yeah. Yes. Which is the same thing. That is because if you say NC geometry, but then of course you need to know, right? Interestingly, so here we don't have an object $geometry. Yeah, we have an object called geom. It depends for the NC dataset. It depends on whether you read this North Carolina dataset from the shapefile, and in shapefiles, geometries don't have a name, and then GDAL reads them and always calls them geometry. Shapefiles don't have named geometries. But the default, for me at least, is that I read it as a geopackage. Geopackage is an SQLite spatial database extension, new standard that, same kind of standardization world, a new standard that many people think might be a good replacement for shapefiles. In any case, it's a single file. It's no longer 4 files, and it contains everything. It's an SQLite database. You can open it with SQLite, look at all the tables, do things. We can even read it directly without GDAL, but here GDAL reads this thing because it's just the standard that GDAL supports. So this reads the North Carolina datasets from a geopackage file, and that has named geometry columns. Like I had here a geometry column called WKB_geometry for some reason. Yes, if I read that in through DBI or through anything, then my geometry again is called WKB geometry. Why shouldn't geometries not be named? Yeah, it's in particular convenient if you have more than one geometry column, which PostGIS facilitates. What are you going to do, right? Both column geometry. Yeah. So so geometry is fine, but then of course you're right. The answer here is that I call them geom, and have the same thing. So ST geometry does this same thing. Is a method, but then SF, the SF method for ST_geometry basically says, well, give me, it uses double square brackets, which is the same thing as $, and then asks for the value that is in the SF_column attribute. So SF objects like NC have a number of attributes, and I can talk a bit about them. A couple of them are obvious names because it's a data frame. We see SF is a data frame. Row names also because it's a data frame. Class, obviously, but also SF column, which says which column of mine is the geometry that I should look at, and that is what ST geometry then takes. So you would also use the $ and then attribute blah blah, yes, or the double square brackets. It could be called something completely else, yes, arbitrary names, but they're registered. And that is the kind of thing that dplyr verbs by themselves will throw out, like the class. You will not end up with an SF data frame, but end up with a data frame or even a tibble. Yes? Zero?
Yeah, if you type your NC and then that bracket with 0, it will plot this and works well like this.
Like this? And then a comma? does something, yeah. Yeah, okay, yeah, but it's still a simple feature collection, so it's an SF object. This seems to deselect everything, but then the selector subset method for SF objects makes geometry sticky. If you don't want to have geometry sticky, use data frames. That is the idea. So you can make this into a data frame and say, okay, as.data.frame, and then you get nothing. Oh, sorry, you get, does this work? You get an empty data frame. So it first converts it to a data frame, and then you do the zero subset, meaning select no columns, and you get an empty data frame. No sticky geometries anymore. Yeah? So that's the sort of the logic. All the SF methods think that you want to work with geometries and that you want to have geometry sticky. If you don't want to put them in data frames, and it will work out as well. So there is no, like, I'm not preaching that the SF classes is such a good thing to use. It is just, for a lot of cases, more convenient. Yes. But there, like, you can use it at different levels. You can use the geometries, you can use the geometry list columns, you can use the SF feature objects. Yes? Yeah. Yes. Oh, well, continue your question.
So my question is, in computational time, sometimes it takes some time to do some intersection. For example, is it the same problem, or is it faster now because you use C++?
It is faster now, but not because of C++. I will show this to you. There is a recent blog on spatial indexes coming to SF. So this is a blog post of last week on rspatial.org, which has a lot of blog posts about SF and so on. ArcGeos and SF both use the same, in a sense, use the same library, the Geos library. Geos geometry open source, it stands for. It's the geometry library that was written originally for PostGIS and then sort of made as a standalone thing that everyone could use. High quality code, and it has a lot of things. ArcGeos does not interface everything. One thing it does not interface properly for the things like G intersects and G covers and these kind of things is the spatial indexes. So it has a few functions. It says here antecedents. This is the part that Roger wrote. This is where ArcGeos used spatial indexes. Since a couple of weeks now, SF uses spatial indexes for everything, meaning for all binary logical predicates and all binary geometry generating functions. So that is intersects, covers, etc., and intersection, union, these kind of things. And that makes quite a difference because the operation is, of course, binary, so it is n squared. Right, so if I did my experiments with this little shifted checkerboard, so to speak, or Go board or whatever it is, lots of polygons, and then increasing that and so on. And you nicely see that if you don't index, then you're basically doing all the pairwise comparisons. It's an n squared operation. If you use the index, it becomes n, it becomes linear in the number of polygons, which is, if you have a lot of polygons, which means like 2 weeks or 10 minutes, that kind of difference. So that's a thing. Here you can see it's linear for both intersection, which generates geometries, of course, much more work, and intersects, which is of course much faster. So the trees, STR trees, they are called sort tile recursion trees. It's a particular algorithm that was worked out and worked very well. Kind of a bucket tree, R tree, and that has always been available in Geos and is now sort of working for R as well. the tree is built for one of the arguments. So if you have like an intersection of two things, you might want to think about the order in which you do it, like intersection xy or yx. Yeah, but you can invert these things. Yeah, so. Any other questions right now? Is it, how are we in terms of, okay, then I will just, tell like a couple of minutes more and then we'll have a well-deserved coffee break. Where was I? Right, I was halfway, yes, I was halfway what is this? I was halfway the higher level operations, the summarize and interpolate, etc. And there's an interesting one, st-join, that basically gives you the spatial join, right? So you can join, like join does in dplyr, or merge does in base R, based on attribute values, yes, regular, numeric, or factor columns, or something like that, and then it finds records that have matching values, and you have these left, right join, inner join, and so on, meaning what to do if things don't match. That's not so exciting. But st-join does this instead of on attributes, does this on predicates on pairs of geometries, right? And we've seen these predicates. There's a whole list of these predicates, right? There's like quite a handful, 2 hands full of them, right? So the default predicate, the default thing that it will do is use st-intersects, yes? So here's an example. I created this point, not by coincidence, of course I looked it up, but I created this point. Here is this point. Now I want to know sort of which county is this point. Does this point fall in, or are there multiple counties? That can't be true, of course. So I have to juggle a little bit and make that into an SF object. It's only it's now a point, right? It's a simple, it doesn't have a reference system. Even points don't have that. Only when they are combined into a geometry list column, they get a coordinate reference system. So I create a list column of a single point with a coordinate reference system that is equal to the coordinate reference system of NC. I know that these values make sense for this reference system. Looked it up. And then I'm going to put that into an SF object. So I make an attribute, A, give it value 1, and say this is my geometry column. So it's of course a lot of work, but no, you typically don't do that. You typically have collections of features, because that is how spatial tables come. They construct them by hand, but you read them from geopackage files or something like that. And here there is the interesting thing, like here I'm going to ask, now give me the spatial join of this point, right, and my set of counties. And that gives me a simple feature collection with 1 feature and 15 fields, right? So I get the point geometry, and the point is this point, as you see, but I get all the properties. So I get the properties of the first object, that is this A field, A is 1, and I get all the corresponding properties of the other objects here, area, perimeter, county, county ID, and so on, for this particular county in which this point falls, right? So I do a point in Polygon and a database match of 2 tables, right? Here's a point table, give me the county for which this thing matches, yes? So far so good. What happens if I revert that? If I say, well, for North Carolina, so for these 15 counties, match these 15 counties to this single point. In principle, I get when I leave left is true, I get a left join. That means that I get as many records as I have in NC, so I get back 100 records with 99 missing values for A and 1 catch with the A value of the point, for the county that contains that point. Yeah, that would be the left join, and that's a bit boring. So I said left is false, that means I get an inner join, so I get only those things where I have a match. Yes, or called it full join. I think it's called inner join. I'm not a database person, but what is useful is that what you get back is an object that has geometry of the first argument. So I get the polygon back, right? Where here I got the point back. So this is basically, you get back one of the 2 geometries, but the geometry of the first type. Yes, that is just the decision. I could also give 2 geometry columns back, but when you then do another join, then you have 4 geometry columns, and I didn't see any point in doing that. So that is what it does now. And by reverting the arguments, you get things back. A nice thing is that the stjoin command has a join argument that takes a function, and that takes a Boolean predicate function. So I pass the function st_intersects, so I get intersections by default. But if I would say, well, try st_covers or st_disjoint, no, not disjoint, anything else, then, for instance, st_touches, then I get a different set. So I have 100 counties. If I join them with themselves, I see that I get 590 matches. Yeah, so that's every county with itself and all the neighbors of the county, and all the neighbors are of course there twice, because A and B is an intersection, but for B, A is an intersection. Yeah, so everything is counted double. However, if I would sort of do st_touches, then the overlapping things fall out, so the counties themselves fall out, so I have 100 less. Yes, the self-intersections are now gone. I can look at other kind of neighboring relationships and make a function that computes rook neighbors, meaning things that have a linear boundary instead of a point boundary. Right. And that gives me then less values, and I can do that. I can also find out what are the counties where I have a match in a point, and that gives me these. Yeah, so I get here, these are boundaries, these are intersections where counties match in a point. I can say a little bit more about that, but I suggest to do that after the break. Actually, this is quite a cool thing, the st_relate with a particular pattern that you can define, because it gives you kind of an infinite power in terms of the logical sort of connections between ways in which geometries connect. I will say a few words about it after the break. Yeah, so let's have a coffee break and continue in 30 minutes.